So welcome. This is an exciting day, and this is an important opportunity to talk about research directions in AI. So clearly there's a lot of work happening to construct the next generation of AI on campus. That's actually not why we're here. We're here in this panel to talk about all of the implications and ways generative AI can actually impact research itself in many other disciplines. Or the question is, how does generative AI afford researchers in the arts and sciences new opportunities to do their research? So hopefully you'll leave here with some ideas and inspiration. So in my own work, I study unexpected consequences of technology. So generative AI will keep me in business for quite some time. So we're not worried about that. But I can imagine revolutions happening in social science research within the next year or so, because these large language models are a way of actually modeling our own human communications within society. But very few or almost no social science researchers that I'm aware of are actually thinking about that. But yet, in 5 years, that might be how a huge swath of social science research is done. So this panel comes from, will give us many other ideas about generative AI, talk about the way generative AI is in their own research. Let me introduce each one, and they'll come up individually, give a presentation, and then we'll have questions and answers at the end. So our first presenter is going to be Stefano Iacus, Senior Research Scientist and Director of Data Science and Product Research at the Institute of Quantitative Social Science, IQSS, where he works on Dataverse, which many of us know is an open source web application that shares, preserves, cites, explores, and analyzes huge numbers and huge amounts of research data. And he'll talk more about that. Next we'll have Ariel Procaccia. Okay, I'm not Italian, I'm working on it. He's the Gordon McKay Professor of Computer Science. Ariel works on a broad set of problems related to AI, algorithms, economics, and society, and he's helped create systems and platforms that are widely used to solve everyday fair division problems, resettle refugees, and select citizens' assemblies. Chris Stubbs, the Dean of Science and the Samuel Moncher Professor of Physics and of Astronomy. Chris Stubbs' research lies at the intersection between gravitation, cosmology, and particle physics. He uses the methods of observational astronomy to address outstanding questions in fundamental physics. He'll describe how generative AI is impacting that work. And finally, Stephanie Gill will wind out the panel. She's an assistant professor of computer science. She directs the Robotics, Embedded Autonomy, and Communication, or known as the REACT Lab. And her work is on an area of how to get multiple robots to coordinate and control, and how control works in such a system. She'll be presenting on generative AI for multi-robot autonomy. And with that, let me turn it over to our panel.
Okay, so thank you, Latanya. So I will talk about these two applications of generative AI, mainly LLMs, to Dataverse and research projects that I'm working on. So on Dataverse, as you know, it's a research data repository, which is also becoming one of the sources of these LLMs. And so it creates all the problem for us, as was mentioned in the previous panel, about authorship and what is new and what is not new. Anyway, so let me go through. So we just released a chatbot, which allows the user of Dataverse, this is a standard database page, to interact with the data. So this is in fact an agent based on an LLM, which tries to understand what's inside the data and try to answer questions to the users. So for example, when you open a data set in Dataverse, the first question the chatbot asks itself is, what is this data about? And usually it answers with very silly questions like naming the column names of the tabular data, which is cool, but it's something we don't need an LLM for. And then I can ask questions like, tell me the range of latitudes and longitudes with the highest number of events. So what is happening in the background is try to convert this into a query for the data. And I get some kind of answer. Then the next thing, I can go one step further and say, okay, now map this range of latitudes and longitudes to the name of the countries. So this information is not in the data. And this is where the LLM kicks in. So the training part of the LLM is able to do the mapping for us. And this is one way this tool can be useful. Seems like users of Dataverse is liking this tool. So they are trying to work on their own data and see whether the question they put makes sense for what they actually put in the data. The nice thing is that because of all these advances in open source development, you can write a code of, it's essentially 50 lines of Python. Most of it is about getting the data and creating an application, a visual application for it. It's actually three commands which allow you to run this chatbot for you. So what happens under the hood? Under the hood, what happens is that this model tries to convert this LLM into an SQL query, and from the SQL query, try to get an answer back and transform this into an LLM, natural language sentence. So, of course, the reasoning, which is called the chain of thoughts, becomes more and more interesting as long as you put more interesting questions like who smoked more in this data set, man or woman, and by which amount in which city. So, and you see, essentially what is doing is actually at the end of the chain of thought, the blue lines is about getting SQL answer from this data, and then transform it back to something that human understands. Sometimes it fails, sometimes it tries to correct himself, but it's essentially an agent, an SQL agent. The nice thing is that you can have translation out of the box. So you can put the question in language because these models are actually trained in multiple languages. And so the translation happens automatically, even though, of course, the code internally is all in English. And so you can try all possible languages. For some reason, German doesn't work. Don't ask me why, but other languages work. So the other last thing is that now we recently added some capability of doing statistical analysis. And this is where maybe the authorship problem comes out, because I essentially asked to write something for me. So create a regression analysis where I want to predict this in terms of this other thing. Tell me which variables you have used. Give me the coefficient of regression line and so forth. So this is almost a paper out of someone else's data. And so I don't agree with Melissa that this kind of approach doesn't affect social sciences because you can ask ChatGPT to find the right data to support your own hypothesis, create a model, cherry pick in the model, and give you the table that the social scientists will read. So I think it's a threat that we need to consider also from my perspective. So the other thing what we did is to implement semantic search. So now you are all very expert in this area. So you know that before LLM came out, the standard approach was take a sentence, create a matrix of presence or absence of words in a bag of words system, and create this vector. Pass this vector to any machine learning model and try to guess some results. They have no geometrical construction, and so they cannot be used the same way the embedding, which Melissa was talking about, are now working. So embedding are real vectors in this vector space. The vector space is made up in a way that the closeness of vectors is supposed to have the same meaning in terms of semantic closeness. And so you can interpret geometrically the relationship between these vectors. So in a traditional Dataverse search, which is using the state of the art in, say, in search engines, Solar, Apache, Lucini, if you look by keyword, you get this kind of results. So sometimes you get good results, sometimes not. But if you use semantic embeddings, so semantic search, you get all proper results. And even if you change the query into something which is not exactly what the dataset has in it. So for example, COVID and coronavirus are synonyms, and you can use both if you use semantic search. You cannot use both if you use keyword search, and so forth. And then, of course, again, you have free translation, so you can search in any language. And of course, Dataverse is quite popular around the world. So the other thing I wanted to show very quickly is that things like give me this dataset named Colorado Adoption Project, which is just 3 keywords. It doesn't show up as the first result using this kind of approach, this standard keyword approach. Just because the way the index are built, sometimes it doesn't fit your need. So my curation manager, Sonia, gets crazy about this with my team. And so we try semantic search. Semantic search works a bit better, so at least it's the third result. But if I put the question in a natural language fashion, like the Colorado Adoption Project data, it comes up first. And there on the right-hand side, you can see the distance measure. So essentially, it works. Then, for what concerns research, the typical application for me now is text classification. This is a typical non-scalable task for humans, especially when you go to analyze billions of data, like social media data, for example. And usually there is a bias in the human who do the analysis for you. And there is also this problem of intercoded reliability. So humans cannot agree more than 80% on what they do when they classify any type of text. And so, of course, this is the problem. So how do LLM perform in this context? We tried both text embedding, but then you require a label set or LLM classification. In this case, you don't require a label set, but you have to verify. So training is possible, but not feasible if you have a small research project, because it costs you millions. So what you can do, you can do fine-tuning, of course. And this is what we did. So the other thing to consider is that usually this kind of application is a bit more complex than just the sentiment, positive, negative, and neutral. Usually you have to categorize across 20 macro categories, like in this example, the comparative agent approaches, or 200 and more micro categories. And even for the human, this is very difficult because it's very hard to understand the context. So essentially, vector embeddings plus a traditional machine learning like a model like random forest perform as well as the best super trained XLBERT model for this data. ChatGPT for direct classification works well, but does not scale because of cost, especially if you go to millions of data, at least for my lab. And with fine-tuning, we were able to actually improve our performance. So, for example, we have this old project trying to analyze all Twitter sentiment, let's say, around subjective well-being based on 8 dimensions. This was all manually classified and then scaled with traditional machine learning. Now we extended it to the Human Flourishing Program, which is another IPSS program, where we analyze 43 dimensions. So it's very high dimensional. And we want to analyze all the 10 billion dataset archive that we have at CGA, IQSS. So we ask the LLM to do the classification, will give us some type of confidence. We actually ask the humans to verify the coding by the LLM. And once we have the verification done, we can run this into the LLM. And then that's the last slide. You know, LLM fine-tuning does not add any knowledge, just say activate some neurons, some weights more than others to actually answer your problem. And this is what we get. So if you run, for example, Llama 70 billion, Llama 2 70 billion, or ChatGPT, you see the accuracy is like 30% for Llama and ChatGPT is 38%. But if you start doing fine-tuning, you can go up to 59%, so 60% on the Llama model, which is totally open source. This is something we can do. You cannot do this for ChatGPT. You cannot fine-tune ChatGPT. And it's, of course, running locally, so you don't have the scalability issue. And that's it. So we are also trying Llama 3, and this is what we are doing now for my research. Frank.
While the next speaker is setting up, I'll ask you a quick question, follow up. These tools are really interesting because to what extent can I just use them on any data set? Like if I'm an administrator at Harvard and I got tons of data coming my way, or I've got my own research data, like how useful, can I just use a lot of these tools?
Yeah, definitely, yes. That's what we're trying to push forward, yeah.
Right, I mean, an IQSS will make them available, or is it like, can I?
The tool is available. It's actually It's available on Dataverse, and you can apply this to any other type of tabular data.
Tell them.
Yeah, sorry. Yeah.
Yeah.
Yeah. The tool is available, yeah.
Great.
Hi, everybody. So my name is Ariel Procaccia. I'll be talking about generative social choice. As you can see here, I'm using quite a few AI-generated images in this short talk. It's appropriate, but also a bit spooky, and I think that's also a feature because it reminds us of some of the dangers of using this technology, and I'll allude to that later on. So this is joint work with Sarah, Paul, David, Gilly, Itai, and Manuel. All of us are at Harvard, except for Paul, who was at Harvard during this work and will be joining the Cornell faculty shortly. Okay, so I want to motivate this through, thinking about Brexit. So one kind of maybe arguable way to frame the dilemma facing British voters in 2016 was which policy would best address the UK's deepest problems, right? We have some problems we want to solve. What's the policy we should adopt? And there are basically two options on the table: either do nothing, keep the status quo, or make a clean break with the European Union and make this huge change. But of course, even on the spectrum of relations with the European Union, there are many other intermediate policies that could have been potentially better, could have had more support than these two extremes. And more generally, you could think about many other possible policies that were not considered at all. So for example, you might think about ditching British cuisine for French cuisine, which personally I think would be a pretty good policy. Think about relocating the royal family to California, or a whole bunch of outlandish policies that potentially could have been either good or bad. So what I want to think about is this kind of open-ended question: what is the policy we should adopt? And I want to think of it from the kind of viewpoint of social choice theory, which is the area of math and computer science and political science and economics that thinks about how to aggregate individual preferences or opinions towards collective decisions in a rigorous mathematical way. Now, the issue is that this area is not suited for thinking about these open-ended questions, and I want to argue briefly that LLMs can help address some of the challenges. So one challenge is this issue of unforeseen alternatives, where typically in social choice, we have a fixed predetermined set of alternatives. And what LLMs allow us to do is to generate new alternatives that, like I said, could be potentially better than the ones that were predetermined. The second challenge is unknown preferences. So typically in social choice and real-life elections and many collective decision-making processes, we ask the participants to explicitly express their preferences over the alternatives. But when we have this huge unforeseen set of alternatives, we can't ask people to explicitly vote, right? Usually we ask people to say, what's your favorite alternative? Give me a ranking. But this would be impossible if we consider all possible policies. So what an LLM allows us to do is to take a person's opinion or priorities or values and extrapolate from that, predict from that, what their preferences would be on some alternative that we haven't seen before. Okay. Now, this combination of social choice and LLMs is a bit odd because social choice theory, as I said, is a mathematical theory, and LLMs are notoriously impervious to theoretical analysis. So to combine these two things, we propose this framework that we think of as generative social choice that consists of two steps. The first step is assuming that the LLM can give us perfect answers to certain type of queries. And under that assumption, we want to give hard theoretical mathematical guarantees on properties of the outcome of our process. The second step is recognizing that LLMs will not give us perfect answers to our queries, and then it's about evaluating empirically how well can we answer these queries and showing that we can give reliable answers. And one nice thing about this approach is that it's future-proof in the sense that if we can show plausibility right now, this will only get better and more reliable as LLMs rapidly improve. So we have specifically in our work implemented this kind of framework in the context of a particular type of democratic process. So here the input is survey responses of N participants, which represent their opinion about a particular question. The output, instead of one policy, is a provably representative slate of case statements. So the idea is that we have various opinions, a diverse set of opinions, And we want to kind of represent them using a small, let's say k equals 5, something like that, a small set of opinions that captures the different aspects, the different facets of the opinions of the participants. Okay, that's our goal. We want to do it in a way that's provably representative, according to a rigorous notion of representation. I don't have time in this short talk to go into that, but rest assured that there is such a notion. Now, in the background, we have an algorithm that's working to take these input survey responses and translate them into this provably representative slate of case statements. And the algorithm as building blocks is using queries to this oracle, to this large language model, that in the theoretical part gives us perfect answers to the queries that we're asking it. So, just to give you a taste of what this looks like, let me tell you briefly what the queries that we rely on are. So we essentially think about two types of queries. The first is what we call a discriminative query. The text as input a participant represented by their survey response and the textual statement. And the output is the given participant's level of satisfaction for the given statement. So this is the kind of query that tries to extrapolate, tries to predict a participant's preferences or opinion based on this, this input that we have, giving us some summary of their preferences. The second type of query is more ambitious. It's what we call a generative query. So this takes as input a subset, a group of participants, represented by their survey responses, and an integer whole number R. And it outputs, this is a bit more technical, the statement that maximizes the R highest level of satisfaction among members of the given subset. So intuitively, what this does is it takes as input a group of participants and tries to generate a statement that satisfies as many of the participants as possible. Okay, that's kind of the intuitive interpretation of this. So, in our work, we, kind of following step 2, we work quite a bit to implement these queries and validate that the implementations are reasonably reliable. I won't have time to go into that. But let me just mention that we also implemented the approach end-to-end and ran a pilot. This was in collaboration with OpenAI as part of a project called Democratic Inputs to AI. So we ran it on an AI alignment type question. The question was, to what degree should LLMs be personalized to individual users? And in this pilot, we had 200 participants, 2 groups of 100, both representative of the US population. And we used the first group of 100 to get their opinions on this question and used our process to generate a slate of 5 statements. Then the second sample of 100 people was our validation phase, where we got them to rate the statements produced in the first phase. And then we try to determine how representative these statements actually are of this fresh sample of participants. And we thought the results were pretty encouraging. So as you can see, 75% of people thought the outcome was perfectly representative of their opinion. Another 18% thought it was mostly captured their opinion. So overall, 93% thought it was perfectly or mostly representative. And we have some additional results showing that this kind of result is non-trivial to achieve, that there's really a diversity of opinion that's hard to capture, and other naive baselines will not get this kind of result. So I'll just finish with the take-home message, which is kind of needless to say, generative AI offers new building blocks for democracy. But as I mentioned initially, these AI-based democratic processes can be dangerous. I'm sure we'll hear more in the symposium on issues with fairness, transparency, bias, accountability, and so on. So all of these issues become especially worrisome when you think about these high-stakes, potentially high-stakes democratic processes. And I think this approach that I presented is encouraging in that by building on this kind of more theoretical viewpoint that gives rigorous guarantees, that's able to address some of these concerns about bias and lack of transparency. And I think this potentially takes a first step towards unlocking the potential of AI for democratic innovation. Thanks so much.
That's great, thank you. As we're changing speakers, I'll ask this speaker a question as you're sitting down, and that is, what's the most generalizable thing that you could give to the audience? Is it this amazing idea of the least general these duals, or most specific, as we used to call it in the old AI days, of how you use the two statements? Do you think that generalizes to many other areas of research?
Yeah, so thinking about the sciences more broadly, so I think this actually resonates quite nicely with the previous talk, right? So part of the capabilities we're talking about is basically summarizing opinions, right? Taking a lot of text and kind of summarizing these opinions in a way that is more concise and much easier to process. So I think this is something that was very much a part of the previous talk as well, and we can see more broadly.
It's great.
Okay, thank you. I just thought I'd run through some of the stuff that I've done playing around with these tools in the domain of research and not teaching. So I've used it for code generation in MATLAB and Python. I've used it to write shell scripts. I love Bash. I had it write shell scripts for me. There's a student in our group for whom English is not their first language, and they wrote their first scientific paper draft, and I read that and I just wilted. And I thought, this is gonna take me like a week between the language issues and the paper issues. So I said, do me a favor, take your manuscript and give the following prompt to GPT. You're the editor of a scientific journal. This manuscript was submitted. Please provide thoughtful critique on presentation, act like a reviewer, bring me back the revised version. Took me half a day. So that was a powerful use. I've used it to generate outlines for talks. I gave a talk and a Japanese journalist wanted to talk to me afterwards who didn't speak any English, so I had it translate the PowerPoint into Japanese and sent it. I had it enhance a postdoc hiring ad. And the two things that I'll focus on today are graphics and interactive data browsing. So you may have seen some cool illustrations in things that have come up. I actually wrote a book, so we're going to devolve into shameless plug here for a second. I wrote a book on how scientists transition into doing big projects. MIT Press decided to publish it. I thought that was really cool. That's the illustration they were going to put on the cover. I'm like, really? That's your graphical representation of big collaborative projects? Seriously? So what did I do? I went to GPT and I'm like, give me something about like big science and big collaborations. Yeah, that's more like it. So they couldn't quite put that on the cover, but and if you do want to see what's on the cover, you can go to MIT Press and download the free PDF if you so choose. So it's really good at generating art for talks. I mean, no joke. It's really seriously powerful at generating illustrations. When I'm done being divisional dean, I'm going to go to Chile and work on this big telescope project called the Rubin Observatory, fire-breathing, nation's biggest investment in ground-based astronomy. I was down there in December, and you can tell I've been obsessing at Harvard about AI. And I had been there for 2 days, typing away, writing a bunch of Python code. I'm like, wait a minute, we should be using generative AI for this project, right? So it's got a huge digital camera shown there in real size, with the moon shown on the focal plane, 3.5 gigapixels, ferocious amounts of data. It's going to be commissioned this coming year. And one of the path-breaking tools that we're using for commissioning is this little tiny baby outrigger telescope that you see circled in red. So that one's on the sky and operating using all the software that we're going to use for the real thing. It takes images, it takes spectra. And because at the system level, all the software is coming together with this baby version of the telescope, we do automated reductions, all the data go into some big database, and then we interrogate that with notebooks running Python in a Jupyter environment. So that's like the working system that we have going. And the data come out with the primary identifier being a given image. There's a bunch of metadata and then a directory of all the sources and their attributes, okay? So what we did was to move to a natural language data browsing, much like what was described in the first talk. So rather than sitting there and writing a whole bunch of code and a whole bunch of cells, rather you can just basically phrase a natural language question in the environment of the notebook. There's a utility that makes an API call over to OpenAI, and it actually sends it a representative of the pandas data frame. And what comes back is code that actually runs on your side, runs in the notebook. And what's really cool about that is if you do a bunch of down selects to make a subset of the data, that data structure is persistent in the notebook and accessible. So really what we're doing is a call to OpenAI saying, please write the code that I'm going to run locally. And it's been really, I think, quite encouraging in that respect. I know this isn't terribly readable, but pretty straightforward list of things that you import. You give it the particular day that you're interested in, and then you just enter natural language queries into this prompt, including in an automated way the generation of plots. So you can basically say, the prompt is, can you make me a pie chart of the total integration time for each of the different filters in the beam, where there's a particular image type, and boom, out comes this pie chart. Right now, could I have done that? Yeah. How long would it have taken me? 5 or 10 minutes. How long did this take? 10 seconds. So it's a huge afterburner of productivity enhancement for this sort of dynamic, quantitative, real-time data browsing, sniff around and figure out what's going on kind of data exploration. Another example is to say, and this is a little bit, less trivial, please make a histogram and a normalized cumulative distribution function as separate plots with grid lines of mount image degradation for all exposure times greater than 5 seconds. And boom, there it is. So in terms of sort of system level diagnostics, and it's interesting, I think, in some ways, this really actually changes the way that you think about how you interact with data. So I'll give you one concrete example. The control room of this telescope has a wall of monitors. It's basically this big, with a whole wall of monitors. If you start taking data at this place and the wind speed starts to come up, there's an upper limit of the wind speed during which you can operate the telescope. Otherwise, things shake too much and the dome falls apart. These days, if you were to say, when is the wind likely to hit the limit, you would click through a bunch of screens to try to find the right plot that some engineer thought was going to be useful, which would be time on the horizontal axis, wind speed on the vertical axis, and you'd squint with your eye and try to predict when it was going to hit the wind limit. But if you think about this totally differently, it's like, I don't need walls of monitors. I just need to ask an AI system, I want a prediction with 90% confidence bounds of at what time tonight the wind's going to hit the wind limit. And that is a perfectly tractable problem. It really does actually, in a very serious qualitative way, change the way that you think about interacting with these big systems. So here's my summary. I made this point earlier. It has kind of a jagged edge of performance over various tasks. The production of graphics, I think, is currently a strong point. We used it a lot in that gen ed course regularly. It does a really good job at computer code generation and debugging. And you can do that in a variety of ways. You can run a Python notebook and bounce back and forth and do cut and paste. You can have Copilot as an augmented part of an integrated development environment. Or you can do what we did, which is to actually, within the notebook, make a straightforward, took my colleague a weekend to write the code, better than I did, to just go and make these calls and have it really embedded in the notebook. So I think, to my mind, this thing that we do in the sciences, which is sort of data browsing and trying to get a sense of what automated pipeline you're going to run, it's a huge efficiency boost. And my insurrectionist plan is to infiltrate it into this project in Chile in the coming year. Thank you.
Thank you. So Chris, I'll ask you sort of the same question I've been asking everyone else while we transition to the last speaker. Though there is as Ariel pointed out, there is a theme happening, the generalizability of what you're pointing out is huge.
Yep, I agree. Happy to share.
That's great. Well, that was efficient.
Okay, so hi everyone, I'm Stephanie. So what I'm going to talk about today is the use of generative AI in robotics. And this is more of a forward-thinking kind of a talk to get you thinking about a few ideas of how this could be used. And I'm also going to talk about a few of the challenges where we really have to think about how these tools, and when I say we, I mean the researchers that are doing the work in robotics and thinking about how these tools can be incorporated. And so I'll try to outline and give you a sense of what some of those challenges are. And I'll end by summarizing a few of the projects in my group where we are starting to think about this and where we're using those tools. So in my work, we think about the use of AI and possibly generative AI in the way that it pertains to autonomy and robotics. So let me explain what that means. And to explain that, I'm going to use a picture here of a robot on one side, and on the other side, what's happening under the hood. So what's happening inside the algorithms that the robot is running. So the important piece here is the decision making. So robots will often have sensors on board that allow it to perceive the environment. So those are the inputs. Other inputs could be communication, so it's communicating with other robots, it's communicating possibly with a cloud that's giving it data. All of that is going into a decision-making framework and outcome actions. So this robot is going to actuate in the world around it. It's going to decide where to go, how to act, what to possibly grab in the environment if it has manipulators. So that's overall the way that I want you to think about autonomy and robotics, and in particular, autonomy is how can the robot do a lot of this on its own without necessarily a human in the loop. So a few examples of autonomous systems, just to drive this home a little bit more, are, for example, autonomous vehicles. Autonomous vehicles are sensing their environment. They're possibly sensing information about other agents, other vehicles, pedestrians, bicycles, anything that it might need to reason about. Possibly also a cloud. Delivery robots that need to coordinate and strategize how to deliver packages across a city. So this is a forward-thinking vision, of course. And also search and rescue. So the idea that in the future, robots can work with humans, with emergency responders, to be able to actually respond and decrease response times, increase the amount of information that emergency responders have about the situation at hand, et cetera. So these are some examples of how robots and autonomy are coming into the world around us and what researchers are thinking of in terms of motivation of the algorithms. Okay, so now what about autonomy in the real world and what can go wrong? So some of the examples of autonomy in the real world are with autonomous vehicles. And I would say that probably this is one of the most prominent examples right now. And you see some of the hiccups in the news. So for example, sometimes autonomous systems will have a lack of understanding of long-term consequences of action. So for example, in some cases, autonomous vehicles have blocked, for example, the path of an emergency response vehicle. So in this case, an autonomous vehicle blocked the way of an ambulance that was trying to get to a hospital. So although the autonomous vehicle might think that this is not a risky action, it does not have the capability to reason far enough into the future to understand that indeed this is a risky action because of the forward consequences of this particular action, even though perhaps there wasn't a collision, right? So collision is definitely a risk now, but thinking about risks later in the future is important for autonomous systems. And this lack of common sense, we need autonomous systems to be able to, what we would say in colloquial terms as humans, is have a common sense. So in this case, this was just one case where this failed, in the sense of this was Cruise that had an autonomous vehicle that actually, this was an accident that happened where a car, human-driven car, hit a pedestrian. The pedestrian ended up underneath the Cruise vehicle. So it wasn't the Cruise vehicle that caused the accident. However, the response of the autonomous vehicle was to try to pull over out of the way of oncoming traffic, which made the problem worse, obviously. If a human's driving the car, you might be able to reason about the safety protocol. So maybe I'll block the oncoming traffic and stay put. So we want to be able to do this. And this is indeed even farther where we want to go next. So going beyond autonomous vehicles, we really want to target even more complex scenarios like this one. So here is a DARPA robotics challenge. And the idea here is that you have a robot that you deploy in a hazardous scenario. So for example, after after a nuclear accident like Fukushima, etc. So now you deploy a robot, it's sensing its environment through its visual field, through its LiDAR, images, etc. And you want it to be able to understand what is happening in the scene. So in this case, the task is it needs to understand that it has to go and actually manipulate the valve in order to be able to perform some tasks. So this DARPA Robotics Challenge is way before we had tools like generative AI. But the point that I'm making with this is that we want to see systems work well autonomously in real world environments, even beyond autonomous vehicle environments to scenarios that are as complex as this one. Okay, so all right, what is happening here? Why is this hard? Why can't systems do this now? Why do we see systems failing sometimes? Now, I should say that autonomous vehicles are working pretty impressively in many ways, but we want to be able to do better if we have these systems working in the real world. Okay, so what's the challenge? I'll put up a little bit of math here just to try to explain what is happening. So right here, we have the control. This is the decision that our robots, our agents are making next in the world. So that's how they're gonna actuate in the world. And this is based on two components that I wanna point out. Some consideration of the current costs that I'm going to incur for performing this action, and some concept of future cost. Now, the way that we would do this algorithmically, and I'm gonna simplify this, but we would think about, okay, how does the state of my agent evolve over time? So you can think of this as the current time. So this first block here is, okay, the immediate consequence of my action would lead to the following cost. And then this piece here, which is the future. So breaking it down, really what this is showing is that these algorithms are going to be considering the immediate consequence of my actions, plus some estimated future consequences of my action. Okay, so what is the problem here? This looks simple. Well, in reality, this is not simple at all. This is actually a very large search space. So even how to represent this search space algorithmically is a huge challenge. And if you think about it, we as humans do this all the time in our heads. We run simulations forward to think about how my actions right now are going to affect me in the future. So why is this hard? What can go wrong? So there are a lot of things that make this difficult, but I'm going to focus on two. One is I can miss some future trajectories. Perhaps there are futures that are possible consequences of my action that are not in my training set, for example. So in the case of the cruise vehicle or the other emergency responder blocking vehicle, perhaps it didn't have that as a potential consequence of its actions when it was simulating forward. Another potential difficulty is that I can terminate too soon. So I don't think far enough into the future, and in the case of autonomous systems, I don't simulate far enough into the future. This, again, is very costly. The farther you look into the future, the more costly it is computationally. So that's why it's difficult. Okay. So the question is, can generative AI help us here? And that's the question that a lot of us are very curious to ask and to answer in our field, in my field of robotics. So can generative AI help? So these tools are new tools that allow us to have higher level reasoning. And so that's very appealing. And so there's already been some work that's been looking at, can we apply LLMs to these driving scenarios? Because it seems that sometimes what is missing is a higher level understanding of a particular scenario. So you have sensor inputs and you have camera inputs. You possibly even have communication with a cloud. So you have maybe even some global understanding, some global data of traffic patterns, et cetera. But then how can I put a picture together that will give us higher level reasoning or give autonomous systems higher level reasoning that humans are good at, but robots are not as good at? So this is the question of, can generative AI help us to better capture the future consequences of immediate actions? And then the second piece is going back to this DARPA Robotics Challenge vision, where you're deploying robots into these disaster scenarios, where this is a pretty complicated scenario. You have to understand that there's a pipe that has been broken that needs to be potentially fixed. Perhaps there's several problems. So what should I fix first? What is more urgent? These are the kinds of questions of, can generative AI help us to better understand the present? They really get a grasp on the current scenario, which is important for planning. Okay, so those are some of the ways that we are interested in exploring generative AI in the space of autonomy and robotics. Now, what are some challenges? I think that, as we've already seen in some of the presentations, one of the big issues with generative AI is reliability. So for example, hallucinations. If I'm playing with ChatGPT and I'm having it summarize some papers to me as part of my literature review, and it fabricates information, this is bad, right? I don't want this. But if this is the input that's going into my autonomous vehicles or my other robots that are actuating in the physical world, this is really bad. So we definitely don't want this. This is a huge challenge for robotics and autonomy. So there are some ideas here that we can exploit that you don't necessarily have with textual data, internet data, and that's the physicality of the system. So these are agents that are actually actuating in space. And so there's been a lot of recent work on, can we use some of the physics of these systems to augment the learning, to augment the machine learning, et cetera, to be able to put physics layers into our architectures, et cetera. So there is some hope along this direction, and we have some more tools at our disposal because of the physicality of the system that might help guide us in the right direction here. Okay, so now I'll just mention a few highlights of how we're using it. So there's a few works in our lab. So this is one. It's actually a work on thinking of future urban mobility and being able to coordinate vehicles to be able to pick up customers that need to be picked up and have rides around a city, for example. And this is some current work with Harvard Evening Van. We also have some recently submitted or recently published work. So actually my student right now is in New Zealand and then going to Japan to present both 2 papers on this topic. But the idea is, okay, how can we use, for example, LLMs? In this case, one idea is to scrape information from the internet to better inform the requests of where people need to be picked up, perhaps because an event has just occurred, this is a popular event or not. Another place where we're using this is for whale observation and rendezvous. This is down in Dominica. And the idea here is that we want agents that we control to actually be able to track whales and have some understanding of where they are even when they're diving and they're underwater, in order to be able to best coordinate agents to go and rendezvous with them, either to tag them for being able to gather more observations, or to just observe them via cameras and video. And lastly, this is some of the recent work that we've done using neural radiance fields, where the idea here is that you have several robots. They're coordinating in their own space, in their own coordinate frame, and they have to put their images together in order to be able to create a 3D model of an object, even from novel viewpoints that haven't been captured in the training set. So how do you do that with multiple robots is what we have been looking at there. So in conclusion, generative AI definitely has the potential to help autonomy and robotics with coordination and better understanding of future consequences. But a big challenge will be reliability. This is even more important, arguably, for actuated systems that are performing actions in the physical world. However, the physicality of these systems can prove to be a key differentiator in being able to really use these tools in the space of autonomy. Thanks. Thank you.
We are at time, so we won't have an opportunity for discussion, though hopefully the panelists can stay afterwards. I do hope that, as you saw, there was quite an interesting breadth and some commonalities about ways in which AI is being used in people's research, and perhaps you can adapt it to ways that you're doing it yourself. I look forward in a couple of years to having you guys up here and see what you've learned from them. Thank you.